Welcome back, ladies and gentlemen. Here we go. In this video we're looking at torque, and I'm going to try to cover a number of ideas related to torque and what it is, what it does. So first, just a definition, a simple one. Easy way I remember what torque really is. It's a force that tends to cause rotation. It causes rotation. Now that's not a very strict definition. A nice stricter definition would be something along the lines of a rotational force that tends to cause an angular acceleration. But let's check something out real easy to grasp. If you can imagine, we're going to either tighten or loosen a nut on a bolt, and we need a wrench to do that. So a wrench is going to grasp these flat sides and there's some length to the handle of the wrench, right? Okay, so you can imagine what's going on here. Hey, not bad. Now, there's a difference here in using the wrench between grasping it way out at its end and trying to rotate things versus grasping it up close and trying to rotate things, or for that matter, not using the wrench at all and pinching it with your fingers and trying to rotate. So the wrench actually is a pretty simple device mechanically. It's just acts as a lever, and it gives you this length of the lever arm with which to you might say gain leverage, right? To give yourself a bit of an advantage. Well, if we apply a force at, say, this location, and we're going to push in this direction with our force, that force is a certain distance away from the axis of rotation right here at the center. So there's a radius there for force 1. And that would produce a different result than if we took the same force and applied it out here at the end, here. So I can possibly just do one of these guys and label that radius for force 2. There's a radius for force 1. So to loosen the nut with a wrench, you can apply a large force that's going to be close to the axis of rotation. You would typically need a larger force there. If you applied the same force further from the axis of rotation, you would actually produce more torque. Or, conversely, you could use less force further from the axis of rotation to achieve the same result as more force closer to the axis of rotation. So you're creating a torque. Now, there's a symbol for torque, and it's just a tau, Greek letter tau. And the torque is created around the axis of rotation. So we have the torque there. Now, it's interesting to note that, I'm sorry, I should mention about torque. The units will be measured in Newton meters. Those are the units of torque that we will use. And so what this implies is you have a force times a distance. Now, it really does matter. There's a little tiny detail we need to make note of here. If the direction of the force is not tangential like this is, right? In other words, if it's not at right angles to a radial line, then we have to take that angle into consideration. So if I redraw this real quick for you, let's see. I'm just going to have a There's the nut. We got the wrench. All right. The business end. Okay. So if we apply a force at the end, or wherever we apply our force, right? But we have in this situation, let's say we're going to grasp the handle here, and we're going to push on the handle. And so we have this radius right there. And I'm going to identify the tangential direction. So here is the tangent direction, so to speak, which is right angles to that radial direction. But we're not going to apply our force there. It's actually somewhat common to have forces applied at just sort of off angles. So there's our force. And we can clearly see that there's an angle we can identify. However, the typical thing that is done, if we extend that radial line, is the angle we measure is here. And so we will have angle theta in that location. Now we could extend lines all over the place, right? In other words, we could see theta here as well. Essentially, angle theta is the angle made between the line of the force and the radial line. Now, there's something interesting if we applied a radial force. If we applied a force at this location but in this direction, well, we actually would not be producing any rotation at all. We would simply be removing the wrench from that nut. Here's the relationship we need. Essentially, it is the tangential component of this force that is going to produce rotation, because the radial component out this direction, well, does nothing for us in terms of causing that turn. So there is our tangential component. F tangential, if you like, and that's the guy that matters. Well, if we make our right triangle, this guy's going to show up over here. Knock that off. So we have a right triangle, and you can see here's theta. So that's the guy we're interested in. It's the opposite of the theta, so we are using the sine function here. And so the torque produced will be equal to the length of the radius wherever we're to the point where we're applying the force. So radius times force times sine of theta. And this gives us the tangential component, essentially, if we look at it this way, right? F sine theta is the tangential component. Awesome. Now, remember, if that theta goes to 0, if we apply that force on a radial line in a radial direction, well, sine of 0 gets you 0, and you produce no torque. All right, cool. Now, along with an amount of torque, there actually is a sign convention also. Like most things that are rotating, it does depend on which way you're viewing it. However, from your point of view, if the torque causes counterclockwise angular acceleration, I'm going to start using that term more. If the torque causes counterclockwise angular acceleration, in other words, alpha that way, or a positive alpha, then what we say is the torque will be greater than 0. In other words, the torque itself will be positive. Conversely, if the torque causes angular acceleration. So this way, or a negative angular acceleration, then the torque is less than 0. In other words, the torque is negative in value. Okay, so just a little sign convention for you. Now, torque actually obeys Newton's second law, just like forces do, linear forces. So we can say that the sum of all torques acting on an object that we're dealing with, we can just call that the net torque if you want, and it's going to tend to produce an angular acceleration in the positive or negative direction. So there's an alpha involved here. Now, if you recall, there's an interesting thing about this. This is producing an alpha, angular acceleration. And now there's a relationship between angular acceleration and a linear acceleration out here, and it's tied together by the radius. So we can work through some business and ultimately get to this right here. This is huge. And it should look very familiar. If torque is analogous to linear force and alpha is analogous to linear acceleration, well, capital I is your moment of inertia, and that's analogous to mass for a non-rotating object. So this essentially is Newton's second law for rotation. All right, and I can show you how we get here. It's pretty straightforward. Recall that from acceleration, net force divided by mass, and also angular acceleration is linear acceleration divided by radius. And we do just do a substitution, and we get this. And there's a little kind of a cheater trick we can do. We can multiply both sides of this by r over r. So I'm multiplying by 1. Multiply by 1 over here, and I get the same thing. And I end up with radius times net force divided by mr squared. Aha! So this is how we're going to show moment of inertia, right? And radius times force, well, that's where we came from to produce a torque. So essentially, we have the net torque, or the sum of all the torques, divided by moment of inertia, will produce an angular acceleration. So, very much analogous to the linear stuff with Newton's second law, forces and accelerations. We have basically rotational force, rotational mass, rotational acceleration, right? Same thing. Kind of a big deal. Okay, let's look at some interesting things that are going on here, though. Workable. There we go. So next I want to revisit static equilibrium. Because we can apply our knowledge of torque to realize, well, we might not be able to answer all the questions we want if we just look at linear information. So previously we defined equilibrium to be the condition where net force acting on an object is 0, right? So sum of forces is 0. That's what we called equilibrium. Well, now we, and also more specifically, we had to look at some of the forces in the y direction and some of the forces in the x direction. Each one of those sort of independently had to be 0. But there's more to it now. We have to add some of the torques, must be 0, to this list. with these two, you essentially get acceleration of 0, both in the x and y direction. With this one here, you essentially get angular acceleration equal to 0. And that's good. That's by definition our equilibrium. So we're expanding what we mean with equilibrium to include rotation. Now here's something important. Note that satisfying one of these conditions, like saying that the sum of forces is 0, does not necessarily satisfy the sum of the torques. And vice versa. The torques can be 0, the net torque can be 0, but you might still have an unbalanced force that's in some linear direction, not causing rotation. Let's look at an example of how this can be useful. So let's check out an automobile. Let's say we've got I don't know, some vehicle looking thing. Here we go. And the vehicle has certain forces acting on it, right? So the vehicle is our object. There is a force here. There is a force here. Two normal forces acting on the vehicle from the ground. The label is force 1, force 2. But there's the weight of the vehicle also, and the weight of the vehicle is acting through what you can call the center of mass. Now we're not going to get into much about center of mass, but essentially the center of mass is the one spot where the weight will act through the vehicle. So if you had to say, if you had to pick one location on the vehicle where you can draw mg, all right, here's the weight, force due to gravity, then it's acting through the center of mass. And so I have some information. Typically on a vehicle where the engine is in the front end, the center of mass is going to be closer to the front than it will the rear. So it's not exactly in the center. It's located more forward because there's more mass in the front. So some information. Typical mass of this vehicle might be 1,800 kilograms. Let's give this thing a wheelbase of 2.5 meters. That's kind of a standard wheelbase in the metric measurement. And let's locate the center of mass. Let's go 1 meter from the front wheel. This is 1 meter horizontally, so I can identify a couple different dimensions here. I have a distance between wheel centers. That's 2.5 meters. And I have a distance from the front wheel to the center of mass, just a horizontal distance here. I'm not going to get into the vertical position of the center of mass. That's going to be a little more than we need to worry about. So I have 1 meter distance horizontally from the front wheel to the center of mass. I have 2.5 meters horizontally from one wheel to the other. And that's what we mean by wheelbase. So we've got some information to work with. I'm interested in finding F1 and F2, the values of those normal forces acting on the car. So here's something that I'm going to have to do. I can easily see that the sum of the forces vertically has to be 0. I want this thing in equilibrium. And so I have two forces acting up and one force acting down. Add them together, I should get 0. Brilliant. With a mass, I can get a weight. So I can know Fg. Not a problem. But I've got two unknowns in this one equation. So I can say, well, sum of forces in the y direction is going to be F1 plus F2 minus weight. And I know that has to equal 0 for equilibrium conditions. Kind of got a little close to my diagram, didn't I? Sorry about that. But I've got two unknowns. That's just an MG. Can't work that out just yet. But there's something else I can use. I can use the sum of torques is equal to 0. That's going to be handy. In order to do this, I have to pick an axis of rotation. My choice is kind of arbitrary. I can pick this location where the force number 1 is applied. I can pick this location where force 2 is applied. It really doesn't matter. It's going to be the same amount of work either way. If I were to pick some other location, it would be more work. I want to pick something nice. For example, why would I pick where this force is applied or where that force is applied? Because this force or that force is 0 distance from that location. And being 0 distance from that location, this force is producing 0 torque if this is the axis of rotation. If I pick this as my point of rotation, this force is producing 0 torque because it's 0 distance away from that location. But which one I pick, it really is not going to make much of a difference. Let's check this out. Let's get this rolling. This is page 4. So I'm going to go to sum of torques equals 0. And so if I can imagine this, there is a torque. I'm going to pick this as my axis of rotation right there. And so it's really going to be kind of coming out of the page at you. This weight is going to tend to produce a torque this way. And this F2 will tend to produce a torque this way. And what I want, what I know, is that those two torques must balance. So they must equal 0. Oh, a little bleed through from the marker, sorry. So how about the torque produced by the weight? That's going to be a clockwise torque, okay, and the torque produced by F2 is going to be a counterclockwise torque. So when I add them together, the torque from 2 minus the torque from gravity should be 0, right? So those two torques should be equal. But a torque is a force times a radial distance, and I have radial distances here. The whole wheelbase is 2.5 meters, so for this weight it is 1.5 meters from that axis of rotation. So this is going to be the force, which is the force of gravity, times the radial distance, 1.5 meters. This torque is the entire 2.5 meters away from, I'm sorry, not the torque, the force is 2.5 meters away from the rotational axis. So that's force times that distance, F2 times 2.5 meters. And this should equal 0. Now the cool thing is, I know that force, or I can easily know it. It's just mg times that 1.5. And so I do have an unknown, it's force number 2. But I only have one unknown. I know m, I know g. So let's solve this. Mass was 1,800 kilograms. And g is just our 9.81. When I work this out, allowing for a bit of rounding, I end up getting 10,600 newtons, roughly. And now that's pretty cool, because what I'm able to do next is come back and see about my sum of forces. Because now I can easily find force of gravity, it's just mg, and I previously had two unknowns. Well, now I've solved for force number 2. I now just have one unknown. I'm going to rewrite that guy. Sum of forces in the y is F1 plus F2 minus g, and that should be 0. And so, force 1 is an unknown. Force 2 I just found 10,600 newtons. And this guy. So mg, what is mg? Just all by itself, that's going to be my 1800. 9.81. And that is right around 26,000, I believe 26,500 newtons. Allowing for a bit of rounding again. And that sum should be 0. Very easily, we can conclude that force number 1 is just about, let's see, well, okay, I've got to subtract that from that. Oh, sorry. Forgive me on that. Blew that math, didn't I? So, mg in this case, you're getting 17,600. 600. Okay, so when we do our subtraction, we're getting 7,000 newtons for force number 1. Okay, watch my math here. So check this out. Recap. There are 3 forces acting on this vehicle. Weight pulling down, and F1 and F2, which are normal forces, pushing up. We are able to surmise the sum of forces is 0 in the vertical direction. However, if we only use linear information, for example, if we just do this, we cannot find the values of F1 and F2 separately because I simply have too many unknowns. But I can use the sum of torques is 0, rotational equilibrium, torque counterclockwise and torque clockwise must cancel because the car is not rotating. And that allows me to solve for those 2 forces independently, which is quite nice. So you want to get a little comfortable with that. Did it matter that I picked the rear wheel as the axis of rotation? Not at all. If I had picked the front wheel, then I simply, if I was rotating here, I would simply have a counterclockwise torque here and a clockwise torque. Oh, just good gravy. Sorry. Clockwise torque here, because that force is going this way, and counterclockwise torque here. But again, those 2 torques would balance, and it would work out, and I get the same answer. Okay, that's all good stuff. But that's equilibrium. What if things don't balance? Let's check that out real quick. There. So, how about some dynamic situations? Things are changing. After all, linear forces tend to cause accelerations when they are not balanced. Torques tend to cause angular accelerations when they are not balanced. Now, to start with, I actually do want to look at a linear situation. So imagine we have 2 objects that are connected. So we have a string here. And let's add a string here. And let's put these objects on some frictionless surface. Maybe the frictionless surface is an air track. That's pretty cool. Get this marker to work. Okay, air track. So, yeah, just a little extra. Okay. No friction. Well, what we're going to do is we're going to pull on this string with a certain tension. We'll call it tension 1. And this can be just mass 1, this can be just mass 2, and that's fine. There will also be tension in this string, tension 2. So pulling on the string to the left causes both carts to accelerate. And the acceleration of the two carts will be the same because they are connected objects. We spent a while studying that last semester. However, it's easy to see that the tension in the two strings are not going to be the same. What we know is that tension number 1 will produce an acceleration in mass 1, but it's also accelerating mass 2. So there we go. Tension number 2 is only affecting this guy, really. And so you have m2 times that acceleration. Well, we want to be able to compare tension 1 and tension 2. Not really solving numerically, but just to make a comparison. Well, since the both masses are experiencing the same acceleration, we can kind of use that to link these two equations together. And so it ends up being that tension 1 divided by m1 plus m2 will be equal to acceleration, right? I just took basically force and divided by mass to equal acceleration. But acceleration is the same, so this force divided by that mass